We have established now that in the marine environment, at least in the surface water, tropical to subtropical ocean, precipitation of a calcite or an aragonite mineral is the rule. But what are the different style of minerals we can have? What are the different cements we can expect in this environment? Well, there are different types of cement that we can expect. Let's start with the magnesium calcite, which is essentially a calcite with a little bit of magnesium into it. And one thing that happens often is actually micritization. So if you have a carbonate grain like a shell or a skeletal component, that skeletal component will be bored by microorganisms, and that will result into a fine-grained carbonate mud known as micrite, and that process is called micritization. And you can see here these nice gastropods. They are relatively recent from the Bahamas, yet they are already micritized. So micritization really starts at the seafloor, and it is one of the earliest diagenetic processes. Here's another example of micrite or micritized component, but this is an ancient sediment, so it's already much more micritized than the previous picture. And then we also have aragonite in seawater, and aragonite forms nice needle-shaped crust around grains. So this is an aragonitic cement, and you can see on the left the fact that we have ooids, those nice rounded ooids, and the cement growing from every ooid towards the center. Whereas on the right picture, it's actually the same thin section, but what it shows with the white arrows is that the extinction of the aragonite cement is exactly the same as the ooid itself, which means that this is an epitaxial cement. It's a cement that grew on top of the ooid, but followed the same plane of minerals, the same mineralogical axes as the grain it grew on, that it nucleated on. And a very typical type of cement that you can find only in shallow marine reefs is this fan-shaped cement or botryoidal cements, and that indicates basically a large volume, a large cavity that was filled by a cement. So to have a cement, you need to have ions. That's something that is clear and easy to understand. You need to bring either carbonate ion, or maybe you need to bring silica, or you need to bring whatever the mineral you want to precipitate to the site of precipitation. So seawater is supersaturated in carbonates. Nevertheless, there's not enough carbonates in one pore volume to completely cement that pore. So we need to understand something about fundamental processes that happen and lead to precipitation. And one of the key concepts here is water-rock ratio. So what is water-rock ratio? Well, water-rock ratio is a way of thinking in terms of both the fluid and the rock in the subsurface. And it's an integral way of thinking. In other words, what you do is you look at the rock that you have, you look at its porosity, the amount of volume that you have for the fluid, and you look at how much fluid has circulated through that rock. So let's talk about water-rock ratio and what controls water-rock ratio at geological time scales. And again, you have to think in terms of over time. This is not just an instant, this is over geological time. Well, water-rock ratio, what we can say about it is that diagenesis is proportional to water-rock ratio. Why? It's because the amount of water that your rock sees will determine how much potential you have for dissolution, but also how much potential you have for precipitation of a new mineral phase. The other thing we can say is that water-rock ratio is proportional to the quantity of water. It's very clear that the more water you bring, the more ion you're bringing, so the more your potential, or the higher your potential of precipitation is. And conversely, if you bring a water that is actually very aggressive and can dissolve your rock, the more water you bring, the more dissolution you can have. So water-rock ratio is proportional to the percentage of water, which often comes down to proportional to the porosity of the rock. Now, water-rock ratio is also proportional to flow, because the faster you move that water, the more water the rock will see. So flow is extremely important for water-rock ratio. And finally, water rock ratio is proportional to time. The longer you expose a rock to water, the more time you have to have diagenetic transformation. So water rock ratio is proportional to time. So now that you know what controls water rock ratio and that you know that water rock ratio really controls the potential for diagenesis in rocks, let's try to understand this a bit further by plotting one case. So here's a case where we have a 3D plot that shows a water rock ratio of 0.5. And the point I want to make is that everywhere on this plot, so on this surface plot, the water rock ratio is 0.5. But notice that the x-axis is flow, so the amount of water flowing. The y-axis is porosity fraction, so how much porosity you have relative to the amount of grain, so from 0 to 1. And the vertical axis represents time. So if you have very low porosity fraction, you need a very large amount of time to get a water rock ratio of 0.5. But if you have a very high porosity fraction, you need a very low amount of time to get to 0.5. And of course, you can also vary the flow, which impacts this water rock ratio. So there are multiple ways to get the same water rock ratio. How you get there is not important. What's important is that the water rock ratio determines the potential for diagenetic transformation of your rock. So a very important concept is diagenetic pumping. Now that you know that water rock ratio matters for diagenetic transformation, you also can understand that we need a pump or a way of circulating fluids in the subsurface to produce diagenetic transformations.